SwayamPrabha. Digital India. Educated India.
Hello everyone. Today we are going to start the 7th week of this course. Before we highlight the topics that we'll cover in this week, let us understand where we stand now. We have completed 50% of this course, and in this 50% we have learned what is the premise of finite element method, what is the idea behind finite element method. And then we have also seen that how a method can be formulated based on that idea. We have applied finite element method to some one-dimensional problems representing, say, bar element, representing beam problem. We have also applied finite element method to plane frame and plane truss problem. We know what is the concept of element. We also wrote a small program through which we can handle relatively larger problems with larger degrees of freedom. And through these steps, we also learned the various, through this process, we also learned the various steps involving finite element method. Now, so far our discussion has been in the context of one-dimensional problem. When we say one-dimensional problem, you see truss and plane frame, they may not be categorized as one-dimensional problem. It means, when you say one-dimensional problem, it means that element level equation that we solve, that is essentially one dimension. Okay. Now, this week and next 3 weeks, we'll be talking about two-dimensional problem, finite element method in two-dimensional problem. Now, FEM in two-dimensional problem is a different situation altogether. It doesn't mean that the premise will change, the essence of finite element method will remain same, but because of the higher dimensions, some of the things which was relatively easier, relatively straightforward in case of one-dimensional problem, things are slightly different here. So we need to deal with those things in a different way. So let us start. We have seen these are the steps involved in finite element method. We have seen these steps several times, but these steps are so important that probably I'll be showing the same slide several more times in coming weeks. So we have we have a boundary value problem. We have already seen if the boundary value problem for one-dimensional boundary value problem, how to formulate the weak formulation, and then how this weak formulation, based on this weak formulation, finite element framework to be developed. Now in today and this week and the next few weeks, we will be talking about boundary value problems in two-dimensional. In this week, we will not discuss anything about weak formulation of two-dimensional problem, two-dimensional boundary value problem. This we will discuss in the subsequent weeks. Now then, we have to discretize the domain. In one dimension, discretization of the domain was very straightforward. In two dimension, the discretization of domain will look like this. This is just to get a feel about two-dimensional in finite element meshing in two dimension. These are some elements we have in higher dimension, in two dimension. Now, they are in this is the most basic element that we can have in two dimension, where we have only 3 nodes. These are the 3 nodes, and this element is called 3-node triangle. Similarly, we can have 6-node triangle, we can have 4-node quadrilateral, we can 8-node quadrilateral, and so on. This is not all in whole. There are many other elements available we can constitute. This is just for representation. Now, next is So this is finite element discretization in two dimension. Now, so next is the derivation of element equation. This one. It is this step where we will see that considerable changes from one dimension to two dimension. Even from two dimension, we will move on to three dimension. We will see that our discussion this week and next few weeks will be, majority of the discussion will focus on this step, derivation of the element equation. Then once we have the element level equation, the rest is assembling of this equation to get the global set of equations, global matrices, global set of equations, and then imposition of boundary condition and solution. Those steps are more or less similar. Now, so let's see, just to let us revisit some of the things that we have already discussed. We know what is the variational statement of a problem. Any problem, we start with a boundary value problem, and then that boundary value problem can be represented through this. So this is a bilinear form. This is a linear form. Bilinear form will give you the coefficient matrix, or in case of solid mechanics problem, if I have to put in, this bilinear form will give you the stiffness term, and the linear term will give you the forcing term, where W is the wet function or trial function, wet function and test function, and U is the trial function. Now the problem is find U such that the above equation holds for any W, which first is a sufficiently continuous. Now when we say sufficiently continuous, it means that it is very subjective. It depends on the what level of continuity, what level of differentiability required for the problem at hand. Okay, we require a different level of continuity. We have already seen it. We require a different level of continuity when we constructed trial and test function for bar problem, and we needed a different level of continuity when we constructed test and trial function for beam element. Okay, so it depends on the governing equations and then subsequent weak form. And then another important criteria is satisfy the specified homogeneous form of the essential boundary conditions that we have on U. Okay, so this is the variational problem we have. Now what we do actually, there are two. Now this equation needs to be satisfied over every element. When we satisfy this equation over every element, what we get a set of algebraic equations. We set an n algebraic equations where n is the number of nodes we have in the element. Now from this statement, variational problem, to and then finally get the set of n equations, n algebraic equations. In between this, there are few things that we perform. And what are those few things? Now, if we need to have an approximation of this test and trial function, right? Now, if we follow Rayleigh's procedure, then the trial function is approximated as this, and the test function is approximated as like this, and when phi are the safe functions. Okay. Now these safe functions, the phi are called the safe functions for an element, and then uj are the nodal values. Then these nodal values depends on what are your degrees of freedom for a given element we have. Now when we construct these safe functions, there are certain criteria to be satisfied. And what are those criteria? The first criteria is continuity, means it should be sufficiently differentiable as required by the weak form. Completeness, it includes all lower order terms up to the highest order used. Now we will have a separate discussion, a detailed discussion on continuity and completeness, and we will also see that how continuity and completeness is important to get a convergent solution in finite element method. Okay. Then another criteria is interpolation. Interpolation means the interpolate the primary variable. Suppose u is our primary variables, then the safe function must interpolate u. We must interpolate means it should, when we see, this gives you an approximation. This is u are the U are the nodal values at the nodal point, and here through this relation we actually write a function through which this primary variable, the variation of primary variable, can be represented within an element. Now, this variation should be such that when this equation is satisfied at the nodal point, then it should restore the nodal value. That is the interpolation property of a shape function. So we know this. Now, so these are the shape functions we have in one-dimensional problem. If you recall, for two-node bar element, the shape function is linear. This is how the shape function, these functions look like. If we have a three-node bar element, there are three shape functions because you have three nodes here. So this is how the shape functions, the expression of shape functions. And for Euler boundary beam element, you see these are the shape functions. We have 4 degrees of freedom. Now there is a difference between this shape function, the approach we followed while constructing this shape function, and approach we followed while constructing these shape functions, and that is already discussed. Okay, in these shape functions we also approximate the derivatives. So the derivatives are also continuous at the node. So this is how the shape function is constructed. Now the first challenge may not be the correct word. Let us say the first task is, or the first deviation or the first difficulty is, in finite element method in 2D we have these are some elements. Again I repeat, these are some representative elements. We can have many other elements in the element library. Now the first task is to construct shape functions over two-dimensional elements. So constructing shape function for one-dimensional element we had already discussed. It was relatively straightforward, but in case of two dimension, this is one task that we have to do: construction of shape functions over two-dimensional element. Now this is one. Now the second thing is again come to this variational problem. So the first thing we do is we approximate. We find an approximation for U and W. Now, once we have approximation for U and W, then we substitute this approximation in this weak form, and in this weak form involves some integration. For instance, if we take just a model boundary value problem like this, and for this boundary value problem, your weak form look like this. Now, where W and U we have already approximated via shape functions, and then W and U can be replaced by the shape function, and then we have to integrate this over the element where the omega E is the element domain. Now this integration also relatively straightforward in case of one-dimensional problem, but the situation is not the same when we deal with two-dimensional problem. You have to perform this integration over two-dimensional element. And you look at these elements, and some of the elements are like this, and we will see some of the elements it is very difficult to have a closed form integration in closed form over such elements. So in that case we need to look for some alternative technique. And what are these alternative techniques? This alternative technique is the numerical integration. So another task we have to do is numerical integration. So from the weak form, to get the element level equation, set of n algebraic equation, we need to have two important jobs to be done, and one is approximation of test and trial function via shape function, and then the second thing is the numerical integration. Now in this week what we discuss is, we will first see the different element types, triangular, rectangular, quadrilateral, all other possible elements we have, that we will see. We'll have a discussion on the construction of shape function is one important task to be done, but the discussion on construction of shape function cannot be isolated from the discussion on completeness and continuity, because we have seen that shape function should be constructed such that the continuity requirement is satisfied and the continuity and completeness both requirements satisfied. what it means in the context of finite element method, what happens when our say functions, when our approximation is not continuous, when our approximation is not complete, what are the consequences, we will see that. So, and another point that we'll cover in this week is the Gauss quadrature technique for numerical integration. There are many other methods for numerical integration, but the Gauss, for most of the time we will see that our approximations are polynomial. So, for which the Gauss quadrature technique is probably the best we can apply for integrating polynomials. Okay. Now, this is the these are the topics that we will cover in this week. Okay. Now, since today is the first class in this week, whatever understanding we have already constructed shape functions for one-dimensional problem. So, we already know how to do that. So, based on that understanding, let us construct shape function for the most basic element in 2 dimension. The most basic element in 2 dimension is a 3-noded triangle, because 3 nodes are the minimum requirement to have a 2-dimensional figure. So, let us see how to construct it, follow the approach that we already discussed in case of one-dimensional problem. We will construct shape functions for the most basic element. And then in the subsequent discussion, we will take several other elements and then form a generalized method to construct shape functions, right? So, let us take one element, and this element has 3 nodes, and these 3 nodes, suppose this element is the E, any arbitrary element E, and these 3 nodes are 1, 2 and 3. And suppose the values at the node are U1, U could be displacement, it could be any other thing that depends on the degrees of freedom you have in the problem. So, U1, U2 and U3 are the nodal values. Now, these nodal values to be represented, now these information we have at the node. Now, what we want to do is, through this shape function, we need to write an approximation, we need to write a function through which at any arbitrary point within the element, the value u can be computed based on the information at the nodes. Now, suppose the coordinates of these elements are, these nodes are, these are the coordinates of these nodes. Okay. Now, so first we have to start with an approximation. We have just 3 nodes here. So, our approximation should be such that it has 3 unknown, because if we start with an approximation which has more than 3 unknown, we may not be having sufficient equation to determine those unknowns. So, let us start with a polynomial approximation like this. Now, the question is here, we will not discuss, you can put a star mark here, we will come to this point probably in some of the class in this week, some of the lecture in this week, the completeness. You see, completeness is an important aspect in shape function that we already know. Now, the question is, see, completeness and continuity, these things do not fall from sky. Right? We have to ensure it in our approximation. How to ensure that? We will see that. But the question is whether this approximation is complete or not. We will just ask the question now. We will see this approximation is complete or not, and what happens if we find this approximation is not complete, or when it becomes incomplete, and what are the consequences of that. That discussion we will have. Now, for the time being, let us take this approximation. Okay. So, C1, C2, C3 are the unknown constant that we need to determine, and for that we need 3 equations. And what are these 3 equations? 3 equations are 3 information we have, and the information is we know the values at the node. Now, if we satisfy this equation at the node, now this, when we satisfy this equation at the node, this is called interpolating the values at the node. This we will get, finally we will get a shape function, we will get an approximation which will restore the nodal values. Now, if we satisfy this equation at the node number 1, so this is our equation. So, at node number 1, our approximation should should restore the values at node number value at node number 1. Similar can be done in case of node number 2 and then in case of node number 3. So these three equations we have, and we have three unknowns, C1, C2 and C3 we need to determine. Now these three equations can be combined and write like this, right? Now, so from this we can say that C1, C2, C3 are this. Now if we substitute this C1, once you have C1, C2, C3 from this equation, and if we substitute this C1, C2, C3 in this equation, we have the approximation. Let us do that now. So this is the equation we have now, and we know that this equation requires an inverse of this, right? And suppose this inverse of this is this, where AE is the area of the element. Okay. Now, since here these expressions written in terms of x1 and e1, x1, y1, x2, y2 and x3, a3, that's what it is. We have written alpha 1, alpha 2, alpha 3 and so on. But when we actually compute the shape function, derive the shape function for a given element, for that element we already know the coordinates, numerical values are known. So we can substitute that and get the inverse. Now, so this is the inverse we have. Now next is, we know from this equation, this is our u, and if we substitute C1, C2, C3, and C1, C2, C3 we can get from this equation. If we substitute C1, C2, C3 in this equation, what we get is this. Now, so u will be this. Now from this, and now already we know inverse is equal to this, and if we substitute this inverse here, then this becomes this. Now we are almost done, and with some algebraic manipulation, from this equation what we can see is that u is equal to this, and some algebraic manipulation we can show that u is equal to this. Now in this expression, this gives you phi 1, which is the shape function 1 associated with node 1. This gives you shape function 2, means associated with node 2, and this gives you shape function 3. And combining this equation, if we write, this gives you the representation of u over any or at any arbitrary point within the element, and phi the shape function. So you see, the same philosophy we applied to get the shape function for this element. Now let us take an example and then actually compute the shape function, actually get the expression of shape function, and then see whether what are the properties it has, the shape functions have, and how this shape function will look like. Take an example like this. So we know the coordinates are this, and then we know that our u is equal to this. Now if we substitute all the values of coordinate in this, and then we will get e is equal to this. Now once we have this, then this inverse will be this, and then this is the expression of u, and from that we can get our shape function like this. So this is our expression u, and this is our shape function associated with node 1, node 2 and node 3. Now these are the shape functions we can have for a three-noded triangular element. Now let us see what are the properties of this shape function. Okay. Now this is how the shape function look like. The first shape function is it has interpolation property, or which is also, the interpolation can be ensured by having a Kronecker delta property. It means that phi I is equal to delta ij, which means that if you evaluate phi at the node, at that particular node, it will give you 1, and other node it will give you 0. So phi 1 will be 1 at node number 1, and at other node it will be 0. Phi 2 will be 1 at node number 2, other node it will be 0, and phi 3 will be 1 at node number 3, and other node it will be 0. This is how the shape function look like. So this is the Kronecker delta property. We know this is also called interpolation property as well. Now This is one property. Next is, now we know these are the expressions for phi. Let us add them. Okay, and if we add them, what will happen? You see, if you add them, then you will see that this is equal to 1. Now when we added it, then it is for any arbitrary value of x and y, you will see this is equal to 1, and this is a very important property, and this property is called partition of unit property. You see, as I said, even in the first week, what happens, whatever we are doing, essentially that is a representation of a physical system. Okay, we are essentially finding solution of a physical system, but we cannot find the solution, we cannot take the physical system as it is. We need to do several, we have to work on idealization from physical system to the idealized system, simplified system, idealization at the approximation level, idealization at the integration level. So at various steps we do this idealization, but essentially the solution that we get or the equations that we solve, they represent the physical system. Now, what happens to the physical system? That should get reflected in the equation, if our formulation is very close to the physical system. And what happens to the equation? Most of the time, if it is not particularly for a numerical error or something else, now that should represent some physical process. Okay. Now these properties, you see partition of unity property we talk about, then Kronecker delta property we just now mentioned. They also have some physical interpretation. We need to understand the story behind that. We will talk about that physical interpretation of those property when we talk about completeness and continuity. Okay. So this is a very important property. Now, this is, if we add them, then this will give you the this satisfy the partition of unit property. Now we need to compute the, once we have, suppose u are the displacement, then from the displacement we need to compute the strain. Now how do you compute the strain? We differentiate the displacement field with the coordinates. So we need to find out the derivatives of phi with respect to x, we need to find out the derivatives of phi with respect to y. Now derivatives of phi with respect to x look like this, and derivative of phi with respect to y are this. Now if we add them, then if we add them, you will see this is equal to 0, and if we add this, this is also equal to 0. These are important properties of these safe functions. Now, suppose I need to find out strain at a point. So this is the displacement field I have now. Strain, as I said, if we differentiate with respect to the coordinate axis, we will get strain. Now, strains, to find out strain, epsilon xx will be this. So del u del x, u is now replaced by this, and then finally our expression for strain will be this. Similarly, we can have expression for strain as y, as like this, in y direction, and then expression for shear strain will be this. Okay. Now we have just now seen, we already have the expression for phi as a function of x and y, and then from there we have seen what are the derivatives of phi. We have just now seen these are the derivatives of phi, and we have seen all derivatives are constant. These derivatives are constant, which is very obvious because we started with an approximation which are linear in x and y. Okay, so derivatives are constant. Now if we substitute these values here, what we will get is, we will get constant. Now this is a very important observation. It means that this element, within this element, our strain is constant, right? And that's why this element is called constant strain triangle, constant strain triangle or CST. So this is how the safe function can be constructed for the most basic element in 2 dimension. Now, two important. This safe function should be completeness and continuity are the two important property that that set function must satisfy. So before we move on, before we see other elements and then see how to construct shape function for those elements, we'll discuss what is completeness and what is continuity and what happens when your shape function, when your approximation is not complete. That discussion we'll have in the next lecture. Okay, so for today, let us stop here. See you in the next class.